Welcome back. Now, we will begin first looking at some of the properties that we calculated using the dynamics of the trajectories of atoms. The reason I want to take you through that one more time primarily because I want to contrast it from Monte Carlo simulation methods. And Monte Carlo, there is no solution of Newton's law of motion, but what we have done so far, we have essentially looked at Newton's law of motion and how the particles are moving through different time trajectories, and that time trajectory has a lot of information embedded in it. And so, we first start with some of the ideas of our time correlation function, and we want to also look at Monte Carlo simulation and then look at how can we generate dynamic information from randomly generated configurations. And so, that is the set of problem that we want to look at. So, first let us look at what we understood from the velocity autocorrelation function when we solved the Newton's law of motion. So, looking at your slide, we said is that V 0 is the velocity of a particle at time 0 and then at any other time t. So, when we look at the self correlation function, this is why it is called autocorrelation. It is the correlation of particle velocity at one time with the velocity of the same particle at another time. So, we are looking at this decay of the correlation between the particle as it moves out in the phase space. We are also looking in the phase space, we are looking at various state variables, and so we call it state space, and the state is temperature, thermodynamic states. So, we are talking about temperature, volume, pressure, specific heat, and all of those thermodynamic properties. So, in this case, if you look at the dynamics of the different atoms, then you can look at average that and see whether there is a correlation. This autocorrelation with itself over different time steps shows us what is the diffusion of that material at certain point. So, if you consider a solid material, you would see is that diffusion constant is very small because it is sticking to certain locations. However, as you look at the liquid like or when the phase transition happens, then the diffusion, the atoms are moving out, and that diffusion constant or diffusion coefficient can be calculated for different material using velocity autocorrelation function. And that is where we use the formulation of Green-Kubo, where we look at the d 0, which is the diffusion constant, as the integration of velocity autocorrelation function. So, if we integrate at t 0 to t to some time x and we look at the time correlation function, then we can figure out the diffusion constant. However, we can also look at diffusion constant as a parameter for the phase transition. So, if you look at in this slide here with the definition of velocity and diffusion, we are looking at the decay in solid phase. As we said is that in solid there is some diffusion of the atoms, but around their lattice structure. So, there is a lattice position, and if you look at X-ray diffraction of the material, you will see particles at particular location. But if you know that the vibrational frequency at any temperature, the atom is moving around its central position, and that is the local diffusion. So, you can also calculate that diffusivity or diffusion in the solid phase within the crystal structure using velocity autocorrelation function, while it gives you the idea that it is a solid because of the shape of the velocity autocorrelation function, which we call time tail of that. So, if you look at here the velocity autocorrelation function with respect to the potential energy function, first decays down, then goes below 0, becomes negative, then it again goes to positive, and then it becomes asymptotic to the 0 value. This is similar to damped vibration characteristics. In this case, what we are looking at with the formulation, that it shows the positive and negative peaks here show that it is in a solid phase. If we had to look at in a different phase, which is hand drawn here with respect to the potential energy, then the gas phase is represented by a simple exponential decay going towards 0 energy. If you look at liquid, it goes to negative and then become asymptotic to the 0 value, but in case of solid, it shows a sinusoidal damped vibrational behavior, which is very important to understand the phase transition. So, this figure on your slide shows you that just by looking at velocity autocorrelation and plotting it over time and at different state space, that means different thermodynamic conditions, we can tell by the shape that whether the system is in liquid phase, gas phase or solid phase. But we then move further and look at the derivation of harmonic oscillator, which we did last time in last sections, where we looked at simple Newton's laws of motion as a simple harmonic motion, and then we said simple harmonic motion also becomes a harmonic oscillator, and then we can apply the Schrodinger's equation to the harmonic oscillator approximation and see that there are certain rules, what they call selection rules, in case of the electronic energy states, which are the allowed state, and this is where we say there selection rules for the allowed modes of vibration. Now, in this definition I said lot of things, essentially saying that harmonic oscillator, which is coming from the Newtonian model, can be converted into Schrodinger equation, which is quantum mechanical, and from that quantum mechanical we looked at the quantum mechanical phenomena of vibrational modes and vibrational spectroscopy. So, the scientists in vibrational spectroscopy are able to observe by the scattering of the light with IR spectroscopy or Raman spectroscopy, what are the modes of vibration. But those modes of vibration also have very good connectivity with the velocity autocorrelation function, because velocity autocorrelation function essentially is showing the relationship between vibrations of the atoms around their lattices or in different regions of the vibration. The reason that is very, very important fact to know, because once we convert this time domain information into frequency domain, then we start seeing those peaks where particles are moving in low frequency zone or medium frequency zone or even high frequency zone, which is the stretching frequency. And we looked at in the last section, which we look at here, is that the velocity autocorrelation function in its Fourier transform, which does nothing but converting velocity autocorrelation function from time domain to frequency domain. Now, we have what we call power spectra of atoms, which is a generalized vibrational spectrum. So, if you look at in generalized vibrational spectrum, density of state is weighted by the square of the vibrational amplitude, and that is where we are able to get generalized vibrational spectrum, and that is where we were able to obtain from the velocity autocorrelation function at the tau limit goes to infinite. If you look at long time tail of velocity autocorrelation function and take the Fourier transform, then we with cos omega t in the rotational frequencies, then we have vibrational frequency represented, and we are able to look at in case of ice at 210 degrees Kelvin, again that is the state space at atmospheric pressure, room 210 degrees Kelvin, below the freezing temperature of 273, we are able to see all 4 peaks with the generalized vibrational spectrum in terms of lattice vibration between 0 to 100, between 100 to 500 or even 1000, these are the torsional vibrations, because this is a water molecule HOH, and then you are looking at the bending vibrations at around 1500 to 2000 wave numbers. Then we look at the stretching vibration, which are studied quite a bit with the laser Raman spectroscopy or laser IR spectroscopy. So, and also we have correlation or we can look at these vibrational spectra using neutron scattering. We can also look at that spectra using what we call as NMR, nuclear magnetic resonance spectroscopy. So, there is a lot of connectivity now with the experimental data, which is our goal. So, with this we were also looking at the velocity autocorrelation function. So, now this is the dynamic information. So, let me stop here. We will look at some of the ensembles and then we will jump into Monte Carlo simulations. Thank you.